Hello everyone, my name is Matvey Poliszczuk, and in this video I will be going over the MEXT Undergraduate 2016 physics exam. So I will solve and explain every question. Now please note that this is part of a series, and in the Physics 2019 video I give a bit of extra helpful info at the start. But to save time, I'm just going to go right into the questions for this video. So first is question 1, which says, a car accelerates uniformly from rest to a speed v for time t. Find the distance a car travels during the time t. So for this, you just need to know the basic 2D kinematics equations for constant acceleration. Specifically, the one I used is this one right here. I learned these as the so-called Suvat equations. So here, s is the displacement, u is the initial speed, v is the final speed, and t is the change in time. So now we can just plug in the values from the question. So it says that the car accelerates uniformly from rest meaning it isn't moving at the start, so the initial speed u is just equal to 0. The final speed is given as v in the question, and also it says that the time taken is t. So we find that the displacement, meaning the distance the car travels, is equal to 1/2 times v times t, which is option B. Next is question 2, which says a monatomic ideal gas expands from 100 centimeters cubed to 200 centimeters cubed at a constant pressure of 1.0 times 10 to the power 5 pascals. Find the change in the internal energy of the gas. So for this, you need to be familiar with this equation right here, which gives the change in internal energy for a monatomic ideal gas. It is equal to 3/2 times the pressure times the change in volume, or 3/2 times the change in pressure times the volume. And note that this equation requires either the volume or the pressure to be constant. It won't work if they both change. Also, I mentioned this in every video, but it's worth noting that this equation is specifically for a monatomic ideal gas. If you were dealing with, say, a diatomic ideal gas, the equation would be a bit different. But in all the practice exams given by MEXT, any question like this uses monatomic ideal gases. So unless something has changed with the more recent exams, which I don't know if that's the case or not, but hopefully not, you can probably assume that any gas question will work with this equation. Next, note that that for this equation to give the result in joules, the pressure needs to be in pascals and the volume needs to be in meters cubed. These are, of course, the SI units. And it isn't exactly necessary to know this for this question, but as a reminder, joules are in kilogram meters squared per second squared, and pascals are in newtons per meter squared, or kilograms per meter per second squared. And with that, we can now solve the question. It says that the pressure is constant, but the volume changes, so we will use this equation right here. And now you'll notice that this question is actually pretty straightforward. You're simply plugging in values. The only problem is that they give you volume in centimeters cubed, but we want to find it in meters cubed in order to fit with the SI units for joules. Now there are a million different ways you can go about this, and I of course suggest doing whatever method you find works best for you. I'm going to show you how I did the conversion from centimeters cubed to meters cubed, but this is not the only way. But make sure you're careful about it, because at least in my opinion, it's really easy to accidentally lose or gain, a factor of 10. I think that's the whole point of this question. It's to see if you can do the conversion without making an error. So to find the change in volume, we take the final volume minus the initial volume, and that's given in the question, and it's equal to 100 centimeters cubed. To convert to meters cubed, I multiply by the conversion factor right here. 1 meter per 100 centimeters, all cubed. So now I'm left with 100 over 100 cubed meters cubed. 100 cubed is 1 million. And then I divide both the numerator and the denominator by 100, because right now the numerator has 100. So we get 1/10,000, which is equal to 1/10 to the power 4, which is the same as 10 to the power of -4 meters cubed. And that is the change in volume in SI units. Now for pressure, thankfully they already gave it in the question as pascals, so we don't need to do anything here. We can plug in both the values into the equation for change in internal energy. And now we just simplify this a bit. Meters cubed times pascals just gives joules. And 10 to the power of -4 times 10 to the power 5 just gives 10, since, 5 minus 4 is 1, meaning this is actually 10 to the power 1. And of course, if it's the power 1, you can just ignore it. And then we multiply it with the 3/2 that comes from the equation for the change in internal energy of a gas. And we get that the answer is 15 joules, which is option C. Next is question 3, which says, a parallel plate capacitor with a plate separation D has a capacitance C. The capacitor is charged to Q and then disconnected from the battery as shown in figure 1-1. Find the electric field between the plates. So for this, you need to be familiar with a couple of electricity equations. First, we have the equation for finding a charge in a capacitor. So Q equals to C times V, where Q is the charge in the capacitor, C is the capacitance of said capacitor, and V is the voltage across the capacitor. Then we have this equation for finding the electric field strength. So E equals to V over D, where E is the electric field strength, V is the voltage across the two plates of the capacitor, and D is the distance between the two plates of the capacitor. So with that, we can solve this question. And if you know these two equations, then it's actually really straightforward. The question asks for the electric field strength, but the equation that I gave here uses voltage, which is not given in the question. So first we take the initial equation and rearrange it to solve for voltage, which is charge over capacitance. Then we plug that back into this equation for the electric field strength and find that it equals to charge over capacitance times distance, and that matches option F. So next is question 4, which says, in figure 1-2, a box of mass M is on an inclined plane. The angle of incline is theta. The coefficient of static friction between the box and the incline is mu. Find the condition where the box will slide. So for this, you need to be familiar with how friction works, and also more generally the basic force laws. So the equation to find the static friction force is right here. F sub s equals to mu sub s times n. Here, F sub s is the the maximum static friction force. So actually this right here should say maximum. Mu sub s is the coefficient of static friction, and n is the normal force. And in case you forgot from trigonometry, sine of theta divided by cosine of theta is just tangent of theta, and the cotangent of theta is the reciprocal of tangent of theta, which is the same as cosine of theta divided by sine of theta. So now with this, I would highly recommend drawing a force diagram, or of course, if you're writing the exam on paper, then you can just add the force lines to the diagram given in the question. So here, of course, is our box. It has a mass of m, so the force of gravity on the box is mg, where g is the acceleration due to gravity. If we break that up into components that are parallel and perpendicular to the slope, then we find that the part perpendicular to the slope is mg cosine theta, and the part parallel to the slope is mg sine theta. And in both cases, the theta that we're using, which is this angle right here, is the same as this theta over here. Now, if you've done a question like this before, you're probably used to the fact that these two angles are identical. But if you haven't, then this might seem a bit confusing. It's pretty easy to solve the fact that these angles are the same geometrically. But I'm not going to do that here. Instead, I can show an example that can hopefully make it easier to understand why these angles are the same. So to start, suppose a box is just sitting on a horizontal surface. In that case, this angle right here is of course just 0 degrees since it's flat. And this angle right here between the gravity and the perpendicular component of gravity is also 0 degrees, since gravity of course points straight down, and that is perpendicular to the horizontal surface. Now let's incline the surface just a tiny bit. So now this angle right here is really small, just a little bit bigger than 0 degrees. And also this angle in here, if we were to draw the straight down gravity and then the perpendicular component of gravity, this angle would also be very small, just a little bit bigger than 0 degrees. And hopefully you can see that as the slope increases and this angle increases, this angle right here will also increase. And it just so happens that these two angles increase at the exact same rate, which means that the two angles are identical to each other. Again, you can prove geometrically that these angles are the same, but this is a physics exam, not a math exam, so I will leave that as an exercise to the viewer, or you can just memorize that those two angles are always the same for a question like this. So now we can go back to this diagram. We have the normal force, which I labeled as F sub n, which is equal and opposite to the perpendicular force of gravity. And then we have the force of static friction right here. And of course, the static friction is equal to the normal force times the coefficient of static friction. And then we know that the normal force is equal and opposite to the perpendicular component of gravity, meaning that the normal force is equal to mg cosine theta. So we can take that normal force and plug it into the equation for maximum static friction, I should be clear. And so we get that the maximum static friction force is equal to the coefficient of static friction times mg cosine theta. Now, the parallel component of gravity, mg sine theta, is trying to push our box down the incline, while the force of static friction, resists that and keeps the box in place. Of course, the question says to find the condition where the box will slide. And so what that means is we need to find the angle at which mg sine theta becomes greater than mu sub s mg cosine theta, meaning the parallel component of gravity, or the component of gravity that is trying to pull our box down the slope, is greater than the maximum static friction force that keeps our box from sliding down. And now we need to just rearrange this equation to solve for theta. So firstly, we can divide both sides by mg, and that just cancels that out. And so now we have that sine of theta is greater than mu sub s cosine of theta. Now in all of the multiple choice options, mu is isolated, so we're going to do that here. We'll divide both sides by cosine of theta. So we get that sine of theta divided by cosine of theta is greater than mu sub s. And of course, sine of theta divided by cosine of theta is just tangent of theta. And so we find that the condition where the box will slide is when our coefficient of static friction is less than tangent of theta, and that matches option A. Also, one thing to note is that in this step right here, I divided both sides by cosine of theta. However, when you have an inequality like this, you need to be careful. If cosine of theta was negative, then this inequality would actually flip. And if that doesn't make sense, try just replacing sine of theta mu sub s and replace sine of theta and mu sub s with a positive number and cosine of theta with a negative number. And then if you do this operation where you divide both sides by cosine of theta, you will see that the inequality does in fact flip. However, in this question, hopefully you can see that our angle theta will always be between 0 and 90 degrees, which means that cosine theta will always be positive, so you don't have to worry about the inequality flip. But in general, it's something to keep in mind. So next is question 5, which says, an object attached to a spring vibrates with a simple harmonic motion as described in figure 1-3. Here t is time and x is the position of the object. Find the maximum speed for this motion. So for this, you need to know a bit about simple harmonic motion and also a little bit about derivatives. So this equation right here gives the position of an object experiencing simple harmonic motion in terms of time t. So x is the position, t is of course the time, a is the amplitude of the simple harmonic motion, or in other words, the amplitude of the sinusoidal function that describes the simple harmonic motion, and omega is the angular frequency. A way to interpret angular frequency is it's just the speed of the object, but instead of in meters or kilometers or some other unit of distance, it is in terms of radians. So it's how many radians the object is traversing per unit time. Now the way you can find the angular frequency is with this formula over here. And it equals to 2 times pi divided by t, where t is the period of the simple harmonic motion. Next, you need to know that the derivative of sine is just cosine. And if you know the chain rule for derivatives, then you'll also know that if the variable inside is multiplied by a constant, then the derivative will have the cosine multiplied by the constant as well. And then you need to know that if you take the derivative of a function that gives you the displacement or position of an object, then you will get a function that gives you the velocity of that object. Also, hopefully you already know this, but simple harmonic motion is always sinusoidal. In fact, I believe that is how it's defined. It's that it's sinusoidal motion. And also, something to remember from trigonometry is that both sine of theta and cosine of theta are always between -1 and +1. They cannot be greater than -1, or sorry, they cannot be greater than +1, and they cannot be less than -1, at least in terms of real numbers. Okay, so now we can start the question. So the diagram in the question labels these 2 points as t sub 0 and 2 times t sub 0. And this distance right here between those 2 points is half of the period of this function. Now, if we were to look at the entire period, it would be how long it takes for our function to start repeating. And hopefully you can tell that if you start at the very beginning and then go all the way to 2 times t sub 0, then the function starts to repeat, right? Here the function is at 0 and it's going upwards, and then over here the function is also at 0 and it's going upwards. So at that point the function is repeating. So this distance right here is the entire period. And then this distance right here from t sub 0 to 2 times t sub 0 is half that distance, meaning it is half a period. Now that distance equals to 2 times t sub 0 minus t sub 0, which is just t sub 0. And so that means that our period is equal to 2 times t sub 0. Sorry, one second. Yeah, and so then we can use the equation for angular frequency, and we find that it equals to pi divided by t sub 0. And so with that, we can actually write a function for the position of our object. Now, hopefully you can tell in the figure that they gave us, the position of the object matches a sine graph. It starts from 0 at t equals to 0, and it goes upwards all the way it reaches the amplitude A. I didn't actually label it here, but this right here is the amplitude A. And then it goes all the way down to the to negative A. And so that matches the exact way that a sine graph works. And so because of that, we can say that the position of our object in terms of time t is equal to A times sine of the angular frequency times t. And of course, we just found here that the angular frequency is equal to pi divided by t sub 0. So now I have a function for the position of our object, and then we can take its derivative to find a function for the velocity of our object. So using the derivative of sine and the chain rule, we find that the velocity of our object with respect to time is equal to A times pi divided by t sub 0 times cosine of pi divided by t sub 0 times t, which is the time. Now the question asks for the maximum speed, so we need to find when this whole equation equals its maximum, and it's actually pretty straightforward. Now, as I mentioned before, cosine of theta is always between -1 and +1, meaning the greatest number it can ever equal to is just 1. And so if we want to find the greatest speed, then we just set this cosine term to its greatest possible value, which is just 1. And so then if that equals to 1, then we find that the maximum speed is just equal to pi times the amplitude divided by t sub 0, which is option D. Next is the section 2 question, which says, the right half of the xy plane is filled with a uniform magnetic field of magnitude B pointing out of the page as shown in figure 2-1. A charged particle of mass m enters the magnetic field region along the negative x-axis in the positive x direction with speed v. The magnitude of the charge is denoted by q. The trajectory of the particle describes a semicircle as shown in figure 2-1. Answer the following questions. So this is, of course, a question about charges in a magnetic field. The first thing you need to know is the right-hand rule for finding magnetic force finding the magnetic force of a charge inside a magnetic field. So here's a picture to show how the right-hand rule works. And note that this is not the only way to do it. You can even see this picture says version 2. So there are other ways, but this is the one that I use. So basically you hold your right hand out in front of you with your palm facing towards you. Then you stick your thumb out to the right, your index finger points up, and your middle finger points towards you. And those correspond to the magnetic force, the velocity of the charge, and the magnetic field, respectively. So as long as you know the direction of at least two of those things, you can find the direction of the third one. Now, note that this rule is only for if these lines are at right angles to each other. If the force or the velocity is not at a right angle to the magnetic field, then it gets a little bit more complicated than this. And also note that this is for a positive charge. If the charge is instead negative, then the magnetic force will be in the opposite direction to where your thumb is pointing when you use the right-hand rule. Next, you need to know the formula for the force of a magnetic field on a charge, or more simply, the magnetic force. It equals to QVB sine theta. Q is the charge, V is the magnitude of the velocity of the charge, B is the magnetic flux density, or it can also just be called the magnetic field or the magnitude of the magnetic field. And theta is the angle between the direction of velocity and the direction of the field. And notice that if the charge is negative, then the force will also be negative, and that matches what I said about the force being in the opposite direction with the right-hand rule. Next, you need to know the equation for centripetal force. F sub c equals to m times v squared over r. F sub c is the centripetal force, m is the mass of the object, v is the velocity of the object, and r is the radius of the circular path that the object is taking. And then you need to know that the period of centripetal motion is equal to 2 pi r over v, where r is the radius of the circular path of motion, and v is the velocity of the object. So with that, we can start answering the question. So first is part 1, which says, is the charge of the particle positive or negative? So for this, we're going to use the right-hand rule. Consider the particle at point O, right when it enters the magnetic field. The question says that the magnetic field is pointing out of the page. So if you're using the right-hand rule, your middle finger will point out of the page. Then the velocity of the particle is going to the right, so your index finger points to the right. And then if you're doing the right-hand rule correctly, you will see that your thumb points down. This means that if the charge on the particle is positive, then the magnetic force on the particle must be pointing downwards. And also, I should note that, like I said before, the right-hand rule only works if these are all at right angles to each other. And I think you can clearly see that the velocity of our particle is at a right angle to the direction of the magnetic field, right? The magnetic field is pointing out of the page while the velocity is pointing to the right, so they are at right angles to each other, so the right-hand rule applies. Now, if we look at the diagram, we can see that the particle starts curving in a circular path downwards. What this means is that when it enters the magnetic field, a force pushes down on the charge. And that force is the magnetic force, meaning that the magnetic force is in fact pointing downwards at point O, which means that the particle has a positive charge, so the correct answer is option A. If instead the particle entered the field and then started curving upwards, that would mean it has a negative charge. Next is part 2, which says find the magnitude of the force on the particle. So for this, we use the equation of the magnetic force on a charged particle inside a magnetic field. It equals to QVB sine theta. Q, V, and B are all just given in the question, while theta is the angle between the direction of the velocity of the particle and the direction of the magnetic field. And as shown in part 1, they are at right angles to each other, meaning the angle is 90 degrees. And hopefully you know that sine of 90 degrees just equals to 1. So the force is just equal to QVB, which matches option E. Next is part 3, which says find the radius of the circular orbit. So the question makes it very clear that the particle moves in a circular path. So you can probably just assume that the magnetic force is in fact a centripetal force. If you want to prove it to yourself though, you can consider the force on the particle at different points along its circular path. So we found earlier with the right-hand rule that at the very top of the circular path over here, the force points downwards. If you use the right-hand rule at different points along the path, you'll see the force always points towards the center of this circular path. So by definition, that means that the force causing this circular motion is a centripetal force. Now that force is of course the magnetic force, which we just found, so we can make the magnetic force equal to the centripetal force, or equal to the formula for centripetal force. Now the question asks to find the radius of the circular orbit. So we just need to rearrange this equation to solve for r. So I bring r to be by itself on the left side, and then you can cancel out one of the velocity terms. And we get that the radius is equal to mv over qb, which matches option D. Next is part 4, which says find the time it takes for the particle to travel from O to P. So for this, we need the formula for the period of centripetal motion, which is 2 pi r over v. We just found r, so we can plug it in here. Cancel out these v terms, and you find that the period is equal to 2 pi m over qb. But remember, we just found the entire period. That is the time it takes for the particle to go around the entire circular path. But the question asks for the time for the particle to travel from O to P. That is only half of the circle, meaning it is half of the period. So actually the correct answer is just pi m over qb, which matches option B. Finally is part 5, which says, now we change the magnitude of the magnetic field from B to 2B and change the value of the particle speed from v to 3v. What multiple of the radius of the original circular orbit is the new radius now after all these changes? Choose the correct answer from the following. So for this, we need to take the radius we originally found and modify it based on the numbers the question gives. So here is the original radius, which I labeled as r sub o, with o for original. Now we find the new radius, r sub n for new, where the velocity is multiplied by 3 and the magnetic field by 2. Take those numbers out, and we find that this just equals to 3 over 2 times the original radius, since this right here is just equal to r sub o. And so the correct answer is A. Next is section 3, which says, a block P of mass m is on a smooth horizontal plane, and an object Q of mass small m is always on top of the block P. Initially, both P and Q are at rest. At a time t equals 0, an initial speed v sub 0 is given to P in the rightward direction. Then Q also starts to move. When a time big T is passed after P is given an initial speed, the velocity of P coincides with the velocity of Q. A coefficient of kinetic friction between P and Q is denoted as mu. Treat the rightward direction as positive, and the acceleration of gravity is denoted as g. Answer the following questions. So this is a kinematics and forces question. Firstly, you need to know the equation for finding the kinetic friction force, which is equal to mu times n. Mu is the coefficient of kinetic friction, and n is the normal force. Then you need to know the basic equations of one-dimensional motion of an object with constant acceleration. I learned these as the so-called Suvat equations. You may have learned them in a different way, but hopefully they're still familiar. So here, v is the final speed, u is the initial speed, s is the displacement, a is the acceleration, and t is the time taken. And there are more equations than this, but I believe, at least for this question, these are probably the only two you're going to need, but you definitely should learned all of the SUVAT equations for the MEXT exam. And then, of course, you need to know that mass is equal to, or sorry, that force is equal to mass times acceleration. And actually, there's a little bit more that you need to know, or at least in terms of how I solve the question. There's also this SUVAT equation. Then also, it is helpful to keep in mind the fact that if you have a function that gives you the position of an object in terms of time, then taking the derivative of that function will give you the velocity in terms of time. And then if you take that velocity function and take the derivative of it with respect to time, you find the function for the acceleration in terms of time. And that is helpful for specifically the last part of this question. So now I can start part one, which says find the force acting on Q at time t is between 0 and big T. So to start, I recommend drawing a force diagram. So we have this block Q right here. It has a gravitational force of small mg that points downwards. And then it has a normal force, F sub n comma Q, and that is equal and opposite to the gravitational force, since it is on a flat horizontal. There's also a horizontal force on Q caused by the friction between blocks Q and P. Of course, the question is, does that force move to the left or right? Now, intuitively, you can probably guess that when block P starts moving to the right, block Q will start moving to the right as well. So the force of friction on block Q points to the right. Now, also note that the question says there is a time big T where the velocities of the two blocks are the same. Now, block P, which is given an initial velocity to the right, clearly will not start moving to the left. It'll get its initial velocity to the right and it'll keep moving to the right until it eventually just decelerates to 0, and realistically it wouldn't start moving to the left after that. That means that both block P and block Q must both be moving to the right at that moment big T. So you can kind of just intuitively deduce that the force of friction on block Q should be to the right. So we can draw that right here. You have a force of friction on block Q and it is pointed to the right. Now the friction force is just equal to the coefficient of friction times the normal force, and we already found that the normal force is equal to mg. So the force acting on Q is mu mg, and that is option A. Next is part 2, which says find the force acting on P at time t between 0 and big T. So you might think to draw a force diagram here, and in general, it is good practice to do so. However, the answer can actually be found very straightforward for this question without a diagram. So to start, notice the question says that block P is on a smooth horizontal plane. Since it is smooth, that means there is no friction between block P and the floor. So then, the only horizontal force acting on block P is the force of friction between blocks P and Q. And if you go back to, when you first started learning physics, what is one of the first things anyone learns about forces? Every action has an equal and opposite reaction. So if the force on block Q is mu mg, then the force on block P is equal and opposite, meaning it is negative mu mg. And so the answer is, of course, negative mu mg, which is option B. Next is part 3, which says find the velocity of P at time t is between 0 and big T. So to find the velocity, you can use one of the SUVAT equations. For that, we can use that force equals to mass times acceleration, and then rearrange to solve for acceleration. Doing this, we find that the acceleration of block P is equal to the force on block P divided by its mass. So it's negative mu small mg divided by big M. Keep in mind, remember there's two different m's. Then we use the equation v equals to u plus a times t, where v is the final velocity, u is the initial velocity, a is the acceleration, and t is the time. The question tells us that the initial velocity of block P is v sub 0, and we just found the acceleration. And so we find that the velocity of block P at a time t is equal to v sub 0 minus small m over big M times mu gt, and that matches option D. Next is part 4, which says, find the expression of big T using some other suitable quantities. So big T is when the two velocities equal to each other. So we have to set the velocity of block P equal to the velocity of block Q. We already just found the velocity of block P. So now we just need to do the same thing as we did before to find the velocity of block Q. So once again, I took the force on block Q and divided it by its mass. And so you get that in order to find the acceleration of block Q, we get that it's just equal to mu times g. And then I use the same Suvat equation as before, this one, in order to find the acceleration on block Q. So the question says that both blocks are initially at rest, and so the initial velocity of block Q is just equal to 0. And so we find that the velocity of block Q at time t is equal to mu gt. And so now we're going to take this and make it equal to the velocity for block P that we found in the previous part. So that's what I did right here. And then at this point, you just want to rearrange and solve for big T, because that's what the question is asking for. So you can see that I brought both terms of big T to the same side, and then I divided both sides such that T is left on its own. And then I have this fraction that's a little bit messy, and basically, I mean, I'm not going to go through every step. You can pause if you want to look at it, but I just I simplified the expression and found eventually that it equals to, let me make sure you can all see exactly what I did. So here, these are the first 3 steps. Again, pause if you want to look more carefully. And sorry, unfortunately, they give us small m and big M, and those two symbols look very similar when I write them by hand. Fortunately, not much I can do there. But eventually, you find that the expression for big T is big M divided by big M plus small m times v sub 0 divided by mu g. And that matches option G. Finally is part 5, which says, find the distance which Q moved against P in the duration from t equals 0 to t equals big T. So it asks us for the distance Q moved against P, or in another way, the distance that Q moved relative to P. To show what this means, let's consider an example. Assume that P is 10 meters long. At the start, Q is at the very end of P. Then let's say that P and Q move in such a way that now Q is right in the middle on top of P. So it is now 5 meters from the ends. If P moved to the right some number of meters, let's say S sub P meters, then that means that Q must have moved 5 less meters than that. If Q moved the same distance as P, then it would still be at the end of P, but it is now in the middle of P, 5 meters from the edge. So moved the distance 5 meters less than P did. So the distance that Q traveled, call it S sub Q, is the distance that S sub P traveled minus 5 meters. Rearrange, and we find that 5 is equal to S sub P minus S sub Q. So now let's consider a more general case. Assume that Q moved x meters down from the edge of P. Previously, we found that this distance 5 was the distance traveled by P minus the distance traveled by Q. Now, instead of the exact number 5, we are using the variable x. This x value, which is the relative position of Q against P, is equal to the distance traveled by P minus the distance traveled by Q. So we now have this equation to find the relative position, which is what the question is asking for. Now technically you can take this equation right now, plug in the values, and so you would plug in the values from this one or maybe one of the other displacement equations from the Suvat equations. You can plug them in right now and try to solve. But I found that it is very difficult to do so. You end up with this pretty big equation that you need to simplify a lot. And it's very easy to make a mistake and end up with the wrong answer. So instead, what we'll do is find the relative velocity first. So remember, we find the displacement with respect to time. And the derivative of the displacement with respect to time gives you the velocity with respect to time. So if we take the derivative of the if we take the derivative of the equation for relative position or relative displacement, we can find the relative velocity. And so you find the relative velocity is just equal to the velocity of p minus the velocity of q. And then you can do the same thing again to find the relative acceleration. Take the derivative of the relative velocity equation, and you will find that it equals to the acceleration of p minus the acceleration of q. So now, with these relative expressions, we can solve for the relative displacement. I am using this Suvat equation. Displacement equals to ut plus 1 over 2 at squared. U is the initial relative velocity, which is the initial velocity of p minus the initial velocity of q. Initial velocity of p is given as v sub 0, and q starts from rest, so its initial velocity is just 0. A is the, this says initial, this shouldn't be here. A is just the relative acceleration, right? I mean, technically initial is correct, but the acceleration is constant, so it doesn't matter if it's initial, final, whatever, it's always the same. It's the relative acceleration, which is the acceleration of p minus the acceleration of q. And we found both of those earlier in the question. And then we are solving at big T, which again we found in the last part. So now that we know what all these values are, we can plug them into our expression and solve. At this point, you just need to expand and simplify, this whole big thing. And as you can see, there's quite a lot here. I'm not going to go through every step, but if you want to see what I did, then you can pause the video and look. So I will make sure it's all visible here. So these are the first few steps. Again, pause the video and take a look if you want to see what I did. And finally, after a whole bunch of expanding and simplifying, you find that the relative distance is equal to big M times v sub 0 squared divided by 2 times big M plus small m times mu g. So next is the section 4 question, which says, two containers A and B of volume V are connected by a thin tube. A cock is equipped in the thin tube and is closed initially. A gas of a pressure P and a temperature T is contained in the container A, and a gas of pressure 2P and a temperature 3T is contained in the container B. The exchange of thermal energies between the gas and the containers may be ignored. The volume of the thin tube may be ignored. The gas may be considered as an ideal gas composed of monatomic molecules. The universal gas constant is denoted as R. Answer the following questions. So this is, of course, a gas and thermodynamics question. You need to know, of course, the ideal gas law, which is that PV is equal to nRT. And you also need to be able to find the internal energy of a gas, which is equal to 3 over 2 times the pressure of the gas times the volume of the gas. Now, there are some other basic thermodynamics or gas equations that can be helpful in this question. And in fact, if you know a few more equations, then pretty much this entire question becomes completely trivial. But because, if you happen to not memorize those equations, I still want to show how you can solve these questions. So I'm only going to use these two, but yeah, just keep in mind if you happen to know some of the other equations, then these questions can be even easier. So first is part 1, which says find the number of moles of the gas contained in container A. So this one's pretty straightforward. We take the ideal gas law, which is PV equals nRT. And I guess I didn't explain it. P is pressure, V is volume, N is number of moles, R is the universal gas constant, and T is the temperature. So we want to find the number of moles. So we just rearrange this equation to solve for moles, PV over RT. In the question, you can see that the pressure, volume, and temperature of A are just P, V, and T. And so the number of moles in container A is just PV over RT, which is option E. The second part says what multiple of the number of moles of the gas contained in container A is there in container B. So we're going to do the same thing here. We're going to use PV equals nRT, except this time we're going to use the pressure, volume, and temperature given for container B. So in container B, the pressure is 2P, the volume is still just the same volume, and the temperature is 3T. And then, so if you solve for T, you get N is equal to 2PV over 3RT. Notice that if you take out the numbers 2 and 3, then you get 2 over 3 times PV over RT. And this, of course, is just the amount of moles that is in container A. That's what we found in the last part. And so that means that container B contains 2 over 3 times the number of moles in container A. And so the answer to part 2 is 2 over 3, which is option F. Next is part 3, which says what multiple of the internal energy of the gas in container A is there in container B? So for this, we'll use the equation to find the internal energy of a gas, which is just 3 over 2 PV. So for the gas in container A, it's just 3 over 2 times P times V. For the gas in container B, we have 2P for the pressure, so it's 3 over 2 times 2P times V. Now if you rearrange for a little, we have 2 times 3 over 2 PV, and of course 3 over 2 PV is just the energy of the gas in container A. So the multiple of the internal energy of the gas in container B is 2 times that of A. And so the correct answer for question 3 is 2, which is option C. Next is part 4, which says, after opening the caulk, the gas in containers A and B eventually reaches equilibrium. Find the temperature of the gas in equilibrium. So before answering this question, I just want to acknowledge you might be tempted to use one of these, shortcut equations like P1V1 equals to P2V2, or I believe it's T1 over V1 is equal to T2 over V2, something like that. But I don't think that these will actually work, because the thing is, for instance, P1V1 equals P2V2 assumes that the temperature and the number of moles is constant between the two, but we don't know what the temperature of the combined gas is, and so that wouldn't work. T1 over V1 equals to T2 over V2 assumes that the number of moles of gas is constant, but again, that wouldn't really work, because when we combine the gases, we now have a different number of moles than what we started with in each of the containers separately. So you can't really do those shortcuts. Maybe there's some other way you could do it that I didn't realize, but as far as I can tell, you have to do a little bit more work. So what we want to do is you want to try to find some of the values for the combined gas. So first we can find the number of moles in the combined gas, what I did right here. So sub C here just means combined. So we take the moles in A and add them to the moles in B, and we found all of those earlier. And so we have that the total number of moles in the combined gas is 5 over 3 times PV over RT. Then what we can do is we can add up the energies of each of the gases in order to find the combined energy. So we already found both of these earlier as well, and we see that it adds up to 9 over 2 PV. Now the reason why this works is because of the very fundamental physics concept of energy conservation. So if we have a certain amount of energy in gas A and a certain amount of energy in gas B, then when we combine them, it'll have the sum of both those energies, because the question says that we can ignore exchange of thermal energy between the gas and the containers, which put in another way means that energy is conserved throughout this whole process. So we have that the total energy is equal to 9 over 2 PV. But what we can also do is we can calculate a bit differently. We can go back to the original energy of a gas equation, or internal energy, which is that it equals to 3 over 2 times the pressure of the gas times the volume of the gas. So we have 3 over 2. So for the combined gas, we have that the energy is equal to 3 over 2 times the combined pressure times the combined volume. And of course, remember that PV is just equal to nRT from the ideal gas law. So we can replace PV here with nRT. So we have that the internal energy of the combined gas is equal to 3 over 2 times the number of moles in the combined gas times R times the temperature of the combined gas. And so since this equals to the energy of the combined gas, and this also equals to the energy of the combined gas, we can just make them equal to each other. So we have 9 over 2 PV equals 3 over 2 N sub C R T sub C. We just found N sub C, so we can sub it in there. And then we're trying to find the temperature of the combined gas. So now you just simplify and rearrange a little. And if you do that, you find that the combined temperature is equal to 9/5 times the original temperature, and that matches option F. And finally is part 5, which says, as in part 4, when the gas reaches equilibrium, after opening the cock, find the pressure of the gas. So again, we're just going to use the ideal gas law. We have PV equals nRT. So if we rearrange, you get that P is equal to nRT over V. And of course, for the gas that's initially in container A, we have that we just have nRT over V, and this is equal to the pressure. And this is important because if you look at the multiple choice options for this question, they want the pressure of the equilibrium gas in terms of the initial pressure, or the pressure in container A. So we have right here, this is what the pressure in container A is equal to. So now what we're going to do is we're going to take the same equation, but we're going to use the combined number of moles of gas. We're going to use the equilibrium temperature, and we're going to use the combined volume. So we have 5/3 times N, and then we also have 9/5 times T, and we have twice the volume. So then now, if you remove all the numbers from it, you find that it equals to this whole thing times nRT over V, and we just showed that nRT over V is just equal to P, the initial pressure, and so we can replace that with just P. And then if you do the simple arithmetic here, you find that it equals to 3/2P, and that is option G, and that is the end of this question. So yeah, pretty easy question, and I mention this every time, but I'll quickly mention it again right now. The question says it's a monatomic ideal gas. As far as I'm aware, for MEXT exams, it is always a monatomic ideal gas. They don't give diatomic or anything like that, so you don't have to worry about it. But technically, if it was not monatomic ideal gas, then this equation would not work. It would be a little bit different. But as far as I'm aware, I don't know for certain. Maybe they changed it in recent years, but as far as I'm aware, you don't have to worry about that. They always give monatomic ideal gases. So next is section 5, which says, as shown in the figure, rectangular glass blocks with an index of refraction of n2 are attached to the upper and lower planes of a rectangular glass block with an index of refraction of n1. A light ray enters the glass block at point A from the vacuum in the incident angle of theta. The light ray reaches point B after repeating total internal reflections in the block. The speed of light in the vacuum is denoted as c. Answer the following questions. So this is, of course, an optics question. First thing you need to know is Snell's law, at least I think it's called that. I might have gotten it wrong, but hopefully you still recognize it. So this law is used to determine the angles of incidence for when light refracts between two mediums with different indexes of refraction. So here, n1 and n2 are the index of refractions of the mediums. So n1 is the medium that the light is initially passing through, and n2 is the index of refraction of the medium that it refracts into. And then theta 1 and theta 2 are the two angles of incidence. So theta 1 is the angle of incidence when the light beam comes into contact with the second medium, and then theta sub 2 is the angle that the light projects outwards from when it enters the second medium. So next important thing to remember is just that the index of refraction in a vacuum is equal to 1. Then you need to know the conditions for total internal refraction, and total internal refraction is just when light reaches a boundary between two mediums, rather than refracting into the second medium, it completely bounces off. And so sometimes it's called total internal reflection. I think total internal refraction and total internal reflection mean the same thing. They're used interchangeably. But basically, for it to even be possible, you need that n1 is greater than n2, where n1 is the medium that the light is traveling through, and n2 is the medium that the light refracts off of. Then you also need to know the critical angle. And basically what this says, this is the smallest angle of incidence for total internal refraction to occur. So this condition here just says that it could be possible for total internal refraction to occur if this condition is satisfied. But then assuming this condition is satisfied, this tells us what is the smallest angle of incidence for said total internal refraction to even occur. So you could satisfy the condition, but still not have total internal refraction if you don't have an angle that is bigger than or equal to the critical angle. So then you need to know that, so this equation gives us the speed of light in a medium. So basically, n is the index of refraction of a certain medium, c is the speed of light in the vacuum, and v is speed of light in that medium. And so with all that, we're able to start answering the question. So first is part 1, which says, an angle of refraction of the light ray entered at point A is denoted as phi. Find the correct expression for sine theta. So if we look at the diagram here, we see that the light enters from a vacuum over here, and it enters with an angle of incidence of theta. And of course, as a reminder, the vacuum has a refractive index that's just equal to 1. And so it enters this new medium, this glass, that has a refractive index of n sub 1, and the angle on this side is phi. So using Snell's law, we see that 1 times sine of theta is equal to n sub 1 times sine of phi. And so we're trying to find an expression for sine of phi. So just rearrange, we find that it equals to sine of theta divided by n sub 1, and that matches option C. Next is question 2, which says, find the condition that n sub 1 and n sub 2 should satisfy in order that total internal refractions take place in the upper and lower planes of the glass block. So for this, I think you just need to memorize the condition for total internal refraction, which, as mentioned before, is that n sub 1 is greater than n sub 2, where n sub 1 is the index of refraction of the medium that the light is passing through, while n sub 2 is the index of refraction of the medium that the light is bouncing off of. So if you look at the diagram, you can clearly see that our light beam is traveling through n sub 1 and is bouncing off of n sub 2, which means that we need n sub 1 to be greater than n sub 2. If we divide both sides by n sub 2, we get that n sub 1 over n sub 2 must be greater than 1, and so the correct answer for this question is C. Next is question 3, which says, find the condition that phi should satisfy in order that total internal reflections take place in the upper and lower panels of the glass block. So here's a diagram of the light beam. Of course, we have the internal angle phi right here. Now, first thing to notice is that this angle right here is exactly the same, right? Because right here we have the angle is between a straight horizontal line and this line of incidence, or like just the line of the light beam. And then on this side, it's the exact same. It's between a straight horizontal line and this light beam line. So they're the exact same angles. And then hopefully you can tell that this whole angle is 90 degrees, meaning that the angle of incidence here is 90 degrees minus phi. And as mentioned earlier, for total internal reflections to take place, sine of the angle of incidence must be greater than n2 or n1. So we have sine of 90 degrees minus phi must be greater than n2 over n1. But if you look at the multiple choice options, phi has to be by itself. It can't be 90 minus phi. It has to just be phi. Now you may remember from trigonometry that sine of 90 minus an angle is just equal to cosine of the angle. So if you happen to remember that, you can already get the right answer. But if you don't know that, you can still figure it out using a bit of trigonometry. So here is a zoomed in part of this section right here. So of course we have the same angles, right? This is phi, this is 90 minus phi. And actually let's label this distance right here as d. And so of course you'll notice that this is a right triangle, right, between the light beam and the distance d forms a right triangle here. Now we're going to assume that the length of the hypotenuse, which is of course this line right here, is just equal to 1. And that's fine because whenever you're doing like trigonometry, you're doing sine and cosine, it only matters on the ratios of side lengths. So you can make the hypotenuse whatever length you want as long as you keep the ratios the same. But the calculations are easiest if you just make it equal to 1. So sine is of course equal to opposite over hypotenuse. So if we take sine of this angle right here, you'll notice that this distance right here is exactly the same as this distance down here, which is d. So we have that sine of 90 minus theta is equal to the opposite, which is d, over the hypotenuse, which is just equal to 1. And so, it's d divided by 1, but of course, if you're dividing by 1, you don't have to include it. So sine of 90 minus phi is just equal to d. And then if we look at this angle right here, and we take the cosine of it, cosine is adjacent over hypotenuse, so adjacent is d, hypotenuse is 1, and so again we have that cosine of phi is just equal to d. And so of course you can see that sine of 90 minus phi is just equal to cosine of phi because they're both equal to d. And so we now have that cosine of phi must be greater than n2 over n1 in order for total internal reflections to take place, and that matches option E. So finally is question 4, which says, find the time at which the light entering at point A reaches point B, penetrating through the glass block. The distance between the two planes, including points A and B, is denoted as L. So once again, we have a diagram here of the light beams. Now, important thing to realize is that when you have internal reflection, the angle of incidence, phi right here, is exactly the same as the, I'm not sure what it's called, the output angle, I guess. These angles are both phi, they're both exactly the same. And so the same thing happens right here. We proved earlier that, this angle right here, phi, is exactly the same as this angle right here, and in the same way you can prove that this angle right here is exactly the same as this one, and so on. So how that all these angles are the same. Now what you can do is you can imagine, let's say we take this section right here, and imagine that you mirror it along this line. And so what you'll have is you'll have this line going down at a certain slope, and then you mirror this part, and it'll just be going down at the exact same slope. It'll just be the same continuous line. And so what you can do is, instead of modeling it as this light beam that reflects several times, you can model it as a single long light beam that's passing through N1 with no reflections or anything. And this works because when light reflects, when it has total internal reflection, there's no change to its speed or angles or anything, and so you can just model it as a single line like this, and it'll still behave the same way, especially since right now we're trying to find the time. And like I said, the speed of the light beam doesn't change when it reflects, and so if you model it this way, you'll still have the same numbers for time if you use this to solve. And this makes it a lot easier because now we just have, this single line, and so we can model this whole path taken as a single right angle triangle. And so since we have phi right here, if you take cosine of phi, you'll have that it equals to L, which is the distance between points A and B, which is given in the question. Or sorry, the distance between, the left and right planes. And that's divided by the hypotenuse, and the hypotenuse is just the entire distance traveled by the light beam. And so we can rearrange and find that the hypotenuse is equal to L over cosine phi. And like I said, that is the distance traveled by the light beam. Next, we have this equation that tells us the speed of the light inside an object with a refractive index. So we have the refractive index of the medium the light is passing through, that's n sub 1, and it equals to c, which is the speed of light in a vacuum, divided by v sub 1, which is the speed of light inside the medium with the refractive index n sub 1. So if you rearrange, we get that the speed of light inside our medium is equal to c divided by n sub 1. And so now we have the distance traveled by the light beam, and we also have the speed of the light as it travels through that distance. So there's a few ways you can go about solving the question from here. The way I like to do it is actually, you can think of it, intuitively, like how did these numbers come together in order to get the final answer, which is time. But what I did was I just looked at the units, right? So this right here, we solve for speed, and clearly speed is in meters per second. It doesn't have to be meters per second, but it's in a unit of distance per unit of time, and meters per second is of course just the SI units. And then when we found the distance here, of course it's a distance, so it's just in meters. And so if you have meters per second, and you also have meters, and we're trying to solve for seconds, I think hopefully you can pretty clearly see that if we take our distance in meters and we divide it by our speed in meters per second, the only unit you will be left with is seconds. And so that's exactly what I did. I took L divided by cosine of phi, which is our distance, and divided it by c divided by n sub 1, which is our speed. And then if you rearrange a little, you get that this equals to L times n sub 1 divided by c cosine phi. And sorry, I forgot to write it, but this is in seconds. And this matches option A. And actually, I rewrote it here to make it a little bit more clear. So we have L over cosine phi in meters, so I wrote meters here, and then our speed is c over n sub 1, and that's in meters per second, so here is meters per second. And then, we're taking a fraction, dividing it by another fraction. That's the same as taking this fraction, multiplying it by the reciprocal of this one. So we have L meters times n sub 1 seconds divided by c meters times cosine of phi. These 2 meters cancel out and we're left with just seconds. So we have the right units at the end, and generally speaking, if you have the right units at the end, you can be pretty confident that you answered the question correctly. So that is it for this exam. I hope you found this helpful. If you have any questions about this exam, leave a comment and I will try to help if possible. And if you are writing the MEXT exam soon, then good luck and have a good day.